Hello, I'm George Flew, the developer of the 3D Toolbox, which is a comprehensive set of tools for designing utility substations in 3D using plain vanilla AutoCAD. You can find details about the 3D Toolbox at my website, www.the3DUtility.com. Today, however, I'm going to demonstrate my latest program, PSSAG. PSSAG is a program for spotting power line poles based on the conductor sag. It calculates a true catenary curve based on the catenary constants derived from the conductor sag design ruling span and tension. Again, PSSAG is not a mechanical line design program, but is intended to aid in spotting poles based upon the conductor sag. Before we begin the demo, let's take a look at the project. As you can see, we have a 69 kV transmission line with a 636 26/7 ACSR conductor with a design tension of 6,000 pounds, a ruling span of 500 feet, and in the medium loading zone. From the drawing, you can see that our project begins with an existing 60-foot Class 2 pole with a TS5G dead-end construction. The pole itself is represented by the cyan line, and these 3 points, which are AutoCAD point entities, represent the 3 phase attachment points. The project also includes an existing ground profile that begins at our project start point, proceeds immediately to a highway crossing, and then through various control points onto the end of the project, which we will see is just over 2 miles in length. So to start, we will clear this off, and then we will bring up our PSSAG program. This opens a form to load our file with our structure data, which we'll look at here momentarily. And then it brings up our basic design form, which includes some areas up here for structures and conductors, and then a number of commands that we can use. And we'll talk about each of these as we go. So first, let's just take a look at the structure setup, and that'll explain a great deal of this information up here at the top. It has the capability to define 4 different structures, and in this case we've used RUS TS type structure. So we've got a TS1, which is a tangent, a TS3, which is an angle structure, and a TS5, which is a vertical dead end. And then we can define here in each of these the distance from the top of the pole to the various conductor attachment points. This is a crossarm structure with insulator string, and then we have a ground clearance, and for 69 kV NESC says 20 feet over fields and roadways, and I've added an extra foot for any inconsistencies in our ground survey. Over here on the right side, then we have some catenary constants, and these are generally associated on the drawing with the conductor positions we're showing here. And at the top of the pole we show the initial sag so that we can look for uplift problems. And then on the bottom phase we will show the final sag, including the clearance to ground, and in this case it's based on a 212 degree F final. And then down here we have determined the minimum pole height for flat terrain TS structure based upon the bottom conductor location, insulator length, our ground clearance, and then the sag of the conductor at the 212 degrees final. And then from a transverse loading calculation, we've come up with a pole class, and of course we've defined a 500-foot ruling span, and then the drawing itself has got a vertical to horizontal ratio of 10:1. Once we're through, we can close, and then that information is transferred through the file. When the program starts, the file's open, it's read, and so you can see here we've got our structures that we defined. We've got it's set up with a standard pole height that we can choose from a range of poles, our 2 catenary constants, and again, if we had included more catenary constants or another structure that were shown up here, we'll show what these 2 check boxes do in a minute, and then we'll talk about these other commands as we go along. And one thing just to point out is these 2 arrows just indicate in which direction our sag or our line design is going, so when it goes to sag it knows which direction to actually draw the sag. So to begin the design, first we want to select our catenary constant that corresponds with our final sag, and then from our commands we will select AutoSag, and then select the lowest conductor attachment point on this first structure, and then it will draw in a pair of catenary curves, one for the conductor and the other that just clears the ground line. Our next command would be auto pole, and we want to make sure we've got our correct pole height, 55 foot, and our correct structure, or TS1, selected, and then we click auto pole, and then it will find the point along this sag curve that corresponds to this lowest conductor attachment point and the intersection of the base of the pole with the ground line. Now, to greatly simplify this, I've combined these two commands into the auto design command, and with this we can move along rather swiftly. So we will use the auto design command as much as possible. So clicking this, it remembers the low point of the last conductor or the last pole that was set in place, and it will remember that unless you do an undo or delete, and then it will prompt you for that point. So we will just keep on with our auto. Our next one, it has picked a point here that's a good ways down this slope, and it's in the steep part of the slope. So I'm going to take the opportunity to use one of our commands, move pole, and I'm going to select the pole and move it up the slope to more of a gentle slope. And it asks me here to update the span, and this is for our own just information at this point, because these blue lines and text is temporary. So moving on, we'll go back and hit the next auto design, and again it remembers the last point on the pole. So even though I move the pole, it remembers its location. And once again, we have another that's on a rather steep slope, so we'll move that again. But again, this is just a matter of using your own engineering judgment to find these optimal locations. So at this point, I'm going to use the auto design once again, but at this point, we're going to change the pole height to 60, since that is our standard height for a TS3, since we're not coming up on this angle. And we'll do auto design again. And at this point, we see that the pole is placed short of our turning point, so we'll do a quick move on that, and we'll move it to the end of our arrow and update our span. And we see that the lowest phase is underneath our sag line, so we'll need to use another command, the replace pole. And let's just start out with a 65. What it will do is it'll replace any structure that you click on. It will replace it with whatever you have currently defined here. So let's do a replace pole, and we can select anything on this pole, and you see here that our sag line is below the lowest attachment point, so this pole is adequate height. Now I'm just going to move through here using auto without a lot of comment, only when necessary. So we will first set this back to our 55 TS1, and then we'll use our auto design button here and just continue to move through the design process. Okay, we've come to another control point here, which is a fence line. Now, we don't want to set our pole in the fence line, but we do want to be inside the fence and close to the fence. We want to be out of the field, but not in the fence line. So I'm going to move this pole to here. And at this point, I want to point out here we have a gentle slope going down to this next control point. So I'm going to use another of our commands, which is the auto span command, and it will it'll take the distance between these two features and divide it up and give us an opportunity to have 3 poles, in this case at 567 feet each. Or we can do 4 poles with 425. I'm going to pick yes and go with the 3 poles, and it will then put each of those 3 poles in. Now let's go back and look at that right quick, and we will see that it actually placed these poles at even spans, but as you might expect, since our average span here is greater than our ruling span, that our 55-foot pole just is not going to quite be enough. So we're trading off fewer poles for taller poles. So we're going to change these, do a replace, and see if we can get by with a 60-foot pole, and we can. And then we'll do another replace, and this one will be a 60-foot. Now, unfortunately, the program is not smart enough to realize this is an angle, so we'll just have to make the change here. And again, we'll leave it at 60 foot in a TS3, since this is a 25-degree angle. Do it again, doing a replace, and we see that 60 is not going to be anywhere near adequate. We probably will have to go as much as 75. So we will, and that's just gauging from where it's hitting on the pole. So we'll do a replace with a 75 and see that we do just clear our conductor sag line with our lowest phase. And with that, we will change our pole height back to our 55 and our structure type to TS1, and continue on with our auto design. This next point is a street crossing, and we don't really need to have a pole, of course, anywhere on that street necessarily, but we do just need to clear it, which of course the auto is going to clear by its very nature. Keep going, and once again we have a downslope pole that we prefer not to do, so we're going to do a move pole, move this up here just to the top of this pole, to the top of the slope. And we see here that pole is much taller than we need there, so we're going to go back and reduce the height on that pole. We possibly could go to a 40 and still get our clearance in this span, but then we've got to deal with this other hill coming up, and so we're going to replace it with a 45. We're going to keep our 45 here, do an auto, and we'll accept that slope is not quite as steep as these others, so we'll accept that. Go back to our 55, do an auto. And now as we come up on this control point, which is an angle, we see that this pole is just too close. It's less than 100 feet away. So let's move it back down slope. One thing, our minimum span needs to be greater than 2/3 of our 500-foot ruling span. So we're going to move this pole down the slope. We'll just pick this high point down here, and then we will go ahead with that. And I want to demonstrate our pole command, and so to do that, what I'm going to do is go back to AutoSAG and select this point for it to AutoSAG, and then I'm looking at the pole here, and it does look like we can get by with a 60, so I'm going to put a 60-foot TS3, and this time I'm just going to select pole, and you see it creates a pole and allows me to drag it to the point. And once again, this point, the low conductor point, is above the sag line, so that pole height is adequate. Going back to our 55, TS1, auto, and then we'll do another auto. And we're getting close to the end of our project. We're close to this dead end, so I'm going to move this pole back. I'm actually going to move both of these poles back slightly, and we'll move this back a little bit more than slightly. Make sure we hit the right line here, not the sag line. And then I'm going to just kind of even out these spans a little. I'm going to move this pole. I don't want to move it too far. We could cause problems in this span. So I'm going to do a move pole, and I'm going to move this back down the slope just a bit, just to kind of even up these spans. And we'll check this right quick. We're doing auto sag from this pole, just to make sure that this 55 is tall enough. So that looks that's good from there. And then we want to do let's change our dead end to 65 TS5 and do an auto. And you'll see that it comes along, and as it looks to find the ground line, the first place it finds is in fact the end of our project. And I see I've over anticipated. Let's change that then to a 60. I don't think we want to go lower than that at this point. So with that, we have made our initial pass on our design, and now the next step is to make a second pass to look for any uplift that we have in our line based on our initial sag. So the first thing we want to do is clear off all these temporary lines that we put in here, and to do that we just click the clean temp, and it will get all of that out of our way. And now we want to go back and, using initial sag, look for uplift. So to do that, we want to go up here and click our initial catenary constant, and then click sag, and we're going to be working on the top attachment points. And what we're looking in each span is to see that our low point of our span, which is indicated by this point feature, we would like it to be in the middle of the span, but what we're looking is that between the two spans, our low points have enough conductor weight in them to meet our mechanical design on this crossarm and insulator. So as we go on down, you can see we have a considerable amount of what we call weight span, and so I again will just move on through this unless I see a need to comment, which I do here. And I want to point out here that oddly enough, the low point of this sag is exactly on this pole. That's not really a problem as long as we have enough weight span here to meet our design criteria. I will point out that you will, if you don't make any correction when in construction, this insulator will tend to swing toward the lower span. So here we'll continue. Again, this is mechanical design to determine whether this is adequate. Unless we run into one that really looks like a problem, we will not hesitate. Now you see here that this low point of this span is actually beyond this pole. But again, as long as these two have enough separation so that there's enough weight in this span to meet your design, you're good. If this point ever passes the point in the next span, then you definitely have an uplift problem, and you need to stop and correct that. So we will continue along. Zoom out here so I can do more at a time. Okay, so there's our second pass, and we see that that we don't have any uplift problems. Possibly one here, but we will again leave that to the mechanical design portion to determine that. The next thing we want to do is go back and lay in our final sag on the low attachment point to again, for two reasons: to make sure that none of the changes we've made are going to affect our ground clearance, and also to allow us to look at the weight span on each one of these poles under final conditions. So we'll select our final catenary constant, final sag catenary constant, and we will begin here. Now you'll notice when I selected that, these two boxes here were checked, and that says we want to show the span, and that's these numbers here. The middle number is actually the actual span between the pole. The number on the left is the portion of the weight span attributed to the previous structure, and on the right is a portion of the weight span that can be attributed to the next structure. So as we go along, if we want to know the total weight span on this structure, we can add up these two numbers here to get that total weight span on that structure. And again, to compare that with our design criteria. So we will, there's really not much to look at here except to verify that we haven't done anything to violate our ground clearance. And I won't even check most of these because they were located such that you wouldn't do that. Now you can see here where we changed these to 60s, that it was necessary because we did increase this above our ruling span. And you see how swiftly this design can go. This is 2 miles, and we've done this in less than 30 minutes. And there's one last thing we need to do to finish up, and that's to come back and show our transition from our tangent to our vertical structures. And to do that, let's take off the show span and ground clearance because we don't want that to show up. And go back to sag, make sure we've got our final sag chosen, of course. And here we're going to go from this, do this bottom to the middle, and then we'll have to click sag again so it knows we're starting over at another point. Otherwise, it'll try to sag back from here to here, which is not what we want. And I'm going to go through here and do these others as quickly as I can. And this video is beginning to run just a little bit long, and we want to get this completed as expeditiously as possible. And there's our completed design from end to end. Now we've got one final command we haven't looked at, and that's our ruling span. And it's a summary of our design. As you can see, our actual ruling span was 519 feet versus our design ruling span of 500 feet, and that works out good. The max span of 718 feet was up under our 150% limit of our ruling span. And our minimum span of 362 feet at 69% of the ruling span was over our minimum of 67%, or 2/3 of the ruling span. And then below that is a summary by pole size and construction type, the number of poles in each category. And that information above is all copied to the clipboard so that you can paste it into a spreadsheet or a report. With that, our design is complete, and as always, if you'd like to contact me with any questions or comments, you can go to www.the3DUtility.com, and in the upper right corner in the menu area, you'll find a contacts menu. And I want to remind you that if you are a public utility, an RUS co-op, or other government public utility, All software on my website is free. And so until next time, thank you and goodbye.